The binary search, it is a searching technique that search a given element, dividing the search interval in hubs. And to apply binary search technique, the list of elements given must be in sorted order, either in ascending or descending order. And it is primarily designed to improve the performance of searching with respect to linear search. In the linear search, we search elements sequentially, means the search element is compared with each and every element of the list. Whenever the element matches, we exit the searching process. But in case of binary search algorithm, the search interval is divided into hubs. So that is why the binary search improves the search performance compared to linear search. So in this video, we will have a look at the algorithm for binary search with the help of some example. Also, we will find the time complexity of the binary search algorithm. For that, I am taking one example of an array. This comprises of 10 elements and all the elements are in sorted order. Now we will apply the binary search algorithm in order to search the element 14 in the given list. The binary search algorithm can be implemented either as a iterative function, or it may also be implemented as a recursive function. However, in this video, we will explore the iterative procedure of binary search. For that, I'm taking an array with the name A, and it has 10 elements. The lowest index of the element is 0, and there are 10 elements, so the last index is 9, and the element to be searched is 14. Let us assume that this element is equals to x. That is x is the element to be searched in the given list. So in order to do the binary search, what we do, first we find the middle of this array. The middle of the array is computed as mid is equals to low plus high. Low means the lowest index, high means the highest index, and divided by 2. And we try to find out x in that position, a of mid. If x is equals to a of mid, then we ends the search, and mid is the position of the search element. This is the position or the location of the searched element in the list. Otherwise, if x is smaller than the middle element, we narrow down our search space into the first half. And if the element to be searched, that is x, is greater than the middle element, then we'll narrow down the search space into the upper half. So here, let me examine this with the help of this example. Here, mid is equals to 0 plus 9 divided by 2, which is equals to 4.5, but it is 4. We have to take the integer part. 4. That means we will search the fourth location. So fourth location we have 12. A mid, which is equals to 12, and the element to be searched is 14. Since 14 element to be searched x is greater than the element located in the middle, a mid, so that is why we need to narrow down, or we need to search in the upper half. In that case, we'll change the value of low now, low and high. Now in that case, since we need to search in this upper half, that's why our low will be now equals to mid plus 1, which is equals to 5, and high will remain as it is. High is equals to 9. Then using these two values, we'll recalculate the value of mid. We'll recalculate the value of mid as low, which is 5 now, plus high, which is 9 divided by 2. 14 by 2 is 7. Then we will go to a mid. In this case, a mid is equals to a7. A7 means 25, this element 25, and the element to be searched is 14. Where 14 is smaller than the mid element. So again we will narrow down our search space into this sub-array, where we'll change the low and high. Low will be as the previous one means low will be equals to 5, and high will be equals to mid minus 1. 7 minus 1, mid is 7. 7 minus 1, which is equals to 6. With this value, again we will calculate the mid for third time. So mid now will be equals to mid 5 plus 6 divided by 11 by 2. 5 by 6 by 2, which is equals to 11 by 2. That gives you 5. So we will go to the fifth location to see fifth location, and now we found out that a mid is equals to 14, and which is equals to the element to be searched x. So here the position or the value of mid, which is equals to 5, is the position of the element to be searched, and our search process ends here. So the same procedure is been explained here. First of all, we have a loop in step number 2, and step number 2.1 we are calculating the mid value, low plus high by 2. Then we are comparing if the low plus high divided by 2, which gives us the mid, and then position the element in the mid position, is it equals to the element to be searched? If it is so, then we will write down that this is end of the, or we will consider that end of the search process, and it returns the value, or we can return the position of that element. Otherwise, if the element to be searched here in 2.3, if x, the element to be searched, is greater than the middle element, then in that case we will move our search space to the upper half, excluding the mid element. So that's why we will do adjust the low value, that is the lowest index, to mid plus 1, and then we'll keep and the high value will remain as it is. And otherwise, if the x, the element to be searched, is smaller, this part indicates if element to be searched x is less than a of mid, then we will restrict our search space to the lower half of the array. That way it will find the position of the element in the given array. Now let's check this algorithm for an element which is not present in the list. Let us say we want to search the element 4, which is not present in the list. Now let us see how this algorithm will work in case the element to be searched is not present in the list. First of all, this is our low pointer, this is the high pointer. Following the norms of binary search, we will compute mid as is equals to low plus plus high divided by 2, which gives us 4. Then we'll find a mid which is equals to 12, and element to be searched is equals to 4. So x is smaller than a mid, so we will narrow down our search space to the left hand side of the array, the first half. In that case, our low will be equals to, as previous, low equals to 0, and high will be equals to mid minus 1, which is 3. Then based on this value, we'll recalculate the value of mid, which gives us 1. Then we will check a1 which is equals to 3, and x is greater than 3, so we will follow our search in the right side of mid. If I want to search in the right side of mid, in that case our low will be equals to mid plus 1, and high will be as the previous one, high will be equals to 3. However, at this point, mid equals to low equals to mid plus 1, which gives us 2. Mid plus 1, which gives us 2. And then again we will recalculate the mid. We will recalculate the mid as 2 plus 3 by 2, 5 by 2, which is 2. Then we will check a of 2, mid is 2, which is equals to 5. And if it is 5, that is 5 is greater than the element to be searched for, so that's why we need to follow the left of mid. That is why low will be equals to previous value of low. Previous value of low was 2, and high will be equals to mid minus 1. Mid is 2, 2 minus 1, which is equals to 1. At this point, low is no longer smaller than high. That's why this loop will terminate. If terminates this loop, that means it comes to the end of this algorithm, and it comes out with the conclusion that the element 4 is not present in the list. This was unsuccessful search of the given element. That way, this algorithm works for both successful as well as unsuccessful search of any element in the given list. Now let us examine the time complexity of the algorithm, binary search algorithm. Let us see how the elements are searched. We will record the locations that is being searched by the algorithm during searching of the element. In the beginning of the algorithm, the value of low is 0 and high is 15, and the mid value computed as 7. That means the first time it will look at the position 7, this element will be searched. Now if the element to be searched is higher than 29, it will go to the right side of the array, otherwise it will go to the left of the array. Or if the element to be searched is in the place 7, that is 29, if we are looking for 29, then the algorithm will terminate. Suppose that element is not 29. If the element to be searched is bigger than the middle element, then it will go to the right side of the array, this side. So in that case, the new array will be from mid plus 1, that is 8 8 to 15, and if we take the mid again, then it will search in location number 11. That is, it will search 46. After that, again that process will continue. If the element is smaller than the element located in 11, it will go to the left side, otherwise it will go to the right side. If it goes to the left side, then it will search in between 8 and 10, so it will search element at position 9. On the other side, it will search at position 13. So this process will go on. Once the element is not located in location number 9, it will go to location number 8, or it will go to location number 10. That way this process continues. On the other side also, it will search if the element is smaller than smaller than the element located in position 7, in this case, which is 29, then it will go to the left side of the array. So then it will search the element from 0 to 6. Middle of 0 to 6 is 3, so it will search the element in location 3. Again that process will continue. It will go to 1, then it will go to 0 and or 2, then it will go to the location 5th. Then if the element is smaller than the element located in location 5th, then it will go to location 4, otherwise it will go to location 6. So that this process will continue, and during the execution of this algorithm, search process follows a tree, and the nodes of the tree are 7. Then in the right side we have 11, left side we have 3. Then that way this tree will be formed. So in order to search an element, how many comparisons are required? That determines the time complexity of the algorithm. Suppose we are looking for the element 46. First it will look at position 7. In 7 we have 29, so 46 is bigger than 29, so we will follow this path. Then we will look at position number 11. Position number 11 is 46. That means it needs two comparisons. Similarly, suppose we are looking for an element 59. In that case, first it will look at position number 7, 29, and the search element is 59. 59 is again greater than 29, so it will follow the right side of the array, and it will go to location 11. In the 11 we have 46. Again the searched element is greater than 46, so it will again follow the right side of the mid element. Right side means from here to here, it will follow here to here, so it will go to position number 13. Position number 13 is 54. 59 is again bigger than the element to be searched, element in position 13, 54, so it will follow this branch. It will go to the right side of the array, then it will look at position number 14, and here in position number 14 we have the element 59, so it will successfully find the elements. And then in that case it needs 1, 2, 3 and 4 comparisons. So at max the number of comparisons required in order to find an element in the array using binary search tree is equal to the height of the tree, which is given as log of n. So since log of n comparisons are required, maximum log of n comparisons are required in order to find an element. That is why the time complexity of the algorithm is given as order of log n. And this is considered as the average case scenario. And in fact, if we if we try to search an element which is not present in the list, for example, if we want to find a element 4 which is not present in the list, it will compare element in position 7, then it will go to position 3, then it will go to position 1, and it will go to position 0. In 0 we find that this element 5, the location element located in 0 is 5, and we are looking for element 4 which is smaller than 5, and then it tries to go out to the left side. In that case it will exit this condition. This condition will not be fulfilled, low, because if we want to move to the left of this node, then we will find from 0 to -1, and in case of 0 to -1, low is not smaller than -1, nor it equals to -1, so the loop will terminate. And at this point it will be concluded that the element is not present in the list. So in case the element is not present in the list, that is considered as a worst case scenario. In that case also, number of comparisons required is equals to log of n, and that's why the time complexity also given as order of log of n. In worst case and average case scenario, the time complexity of the binary search algorithm is order of log n. Now let us check the best case scenario. In the best case scenario, we mean that by best case scenario, we mean that the element is found in the first iteration. That means if we search for a element 29 in the given list, then we'll compare element 7 with the element to be searched, and we found that x is equals to the element located in the mid. So it terminates the algorithm because the element is found. That's why the time required in best case is order of 1. Okay, so that was the time complexity analysis of this algorithm. We have seen that the best case time complexity of the algorithm is order of 1 because it needs only one comparison. Both average and worst case scenario, the number of comparisons is equal. Number of comparisons are equal to the number the height of the tree, and which is given by log of n. That's why the time complexity is order of log n.